Okay, I should be back now. Yeah, okay, and then the thing's working. That's good. All right, so um, left off last time, and I had some interesting ideas, but not really any way to like word them correctly. But I think I, I think I, I think I've collected my thoughts since last time. So I guess I just want to outline a few principles, right? So if we have a computation graph, we have a set of nodes, and the nodes represent essentially like functions that act on their inputs. So in this case, this is a node, and this is it has no inputs. This is also a no input thing, and so these you would classify as knowns, right? I'll just label these. And this acts on four inputs, right? So this is gonna f1, uh, f1, f2, f3, right? And so this you could probably you could classify this as a known or an unknown, depending on what you want to do. So what we really need to do is we need to think about what are knowns and unknowns, right? So like if I hand off this graph, um, we can actually have something even a little bit more advanced. We can say like f5, right? And then this depends on f3 and f4 and whatnot. So if I just hand off like a chunk of this graph to somebody to like compute with, in general, they're limited by the amount of unknowns. And the unknowns, those are going to be like, let's say that we partition this graph like this, right? So, we would hand these off to somebody and hand these off to somebody. The unknowns are going to be um, all the nodes. So I guess I'll write this. Unknowns are nodes that are not knowns. And knowns are nodes. Knowns are nodes. I'm actually going to zoom in a little bit more. Knowns are nodes that have no connections that are coming from that have no connections that are coming from outside our set of knowns. So we have like a set, or I guess I can actually just say our set of nodes, right? Because the idea is that we have this node, and this node, right? Like theoretically, supposedly someone has given us these values, and they've given us like the relationship between these values, and our goal is just to calculate these values. Oh no. So we can say that for like this is a known. This is known. This is actually known, right? Because the idea is that this is a directed graph. So it has no incoming connections. However, this is technically an unknown, right? Oh, wait. I'll color it differently. I'll color it black. So this is an unknown. So these are our knowns, and this is our unknown. We would want to maximize. Oh, okay, but another really important point, right, is that this. So assuming that this is still in the same set, this guy, F6, this guy is also a known. So knowns is like that, and unknowns. So this guy's also a known. Like, we don't know what this, like, the value of f6 is immediately. That's not given to us, but we can find it based purely off the information that we have. So it's a known in that sense. So the thing to do next then is to think about the, like, when we're partitioning a graph of operations, what properties are we trying to, like, partition? So yeah. What properties do we want our partitions to have? And basically, we need to maximize the degree of knowns. Maximize degree of knowns of knowns. Okay. I'm gonna say we want to maximize the amount of connections. Maximize maximize number of connections between knowns. So we want to maximize the number of connections between knowns. We also want to maximize the total number of knowns. We want to maximize the total number of knowns. And we want to minimize connections to minimize connections to unknowns from So I guess the basic intuition that I'm trying to get across is, like, we have a graph full of stuff, and we want to like compact the data as much as we can, right? So we also want to minimize knowns with incoming degree 0. Yeah, so we want to minimize knowns with incoming degree 0. I'm going to edit the stream description. Doing some parallel computing research. Let's say that's more accurate. Okay. So, yeah, okay. So with these in mind, yeah, so I actually think that like these two things, like I'm gonna just I actually think that this I think that this and this are like the two most important things, right? The question is, given an arbitrary computation graph, how do you find the partition that actually like does this? And the other question to answer is, does a good partition graph exist? Does a good like partition exist for all types of problems? And I think the answer to that is probably no. I would say it's probably no, unfortunately. But I know that there are some problems that it definitely would work for. And so I guess my hope is that the kinds of problems that I'm interested in, basically like operations on large matrices, do actually lend themselves to this kind of approach. And the first thing I want to take a look at is like matrix multiplication, mostly because like if that doesn't lend well to it, then I don't know. Then like the whole idea is just kind of screwed. Yeah. Oh yeah. So I guess what I want to do is I can open up PyCharm. And yeah. Cool. Oh yeah, so the last thing I did since last time was I actually like got this to like work and like be like reasonable. Yeah, so now you can see that it actually like puts everything in like reasonable manner. So yeah, I have this graph, right? And I want to figure out how I can split it up so that I'm doing. Oh yeah, I forgot that no one can see the screen. I'm just going to make this smaller, right? So I have this graph, and again, I want to maximize the total amount of knowns, right? So like given a partition or whatever, I want to maximize the total amount of knowns, and I want to minimize connections to unknowns from, or sorry, I want to minimize knowns with incoming degree 0. So the knowns with incoming degree 0 are going to be all of these guys, right? These will, like, no matter what partition they fall in, these will always be by definition knowns. And I want to find the partition that, the correct partition that makes these, the maximum amount of these be knowns as well. Or these and these. Yeah, and so it's like, how do I do that? I don't know. So, my imagining is that unless completely overlooking something, as far as I know, there is no, like, there's not going to be, like, a perfect partitioning, which actually can, like, split it up, perfectly in two, and make, these and these knowns. Well, maybe there is. So, I was doing some reading about parallel matrix multiplication algorithms. Parallel. Oh no, matrix multiplication algorithm. Matrix multiplication algorithm. So what was super interesting is this. So this recursive algorithm, divide and conquer for non-square matrices. I thought this was like super interesting and super promising. Um, Although I don't think that my current computation graph like actually reflects the current thing. So that's all I'm worried about, I guess. So I might be japing myself. Yeah, no, because like, so this graph, I don't know how well it actually corresponds to this, or how well it can correspond. It's certainly very interesting. N, M, and P. Yeah, actually, which case would this fall under? So, oh, I have to look at the code really quick. We have 3, 8, and 5. So the maximum is P. No, the maximum is M. So we would split it like that. So we would split A into a half, and then we would split B into a half. Um, yeah, but this doesn't have the thing where you like add them later, or does it? Does it? I mean, theoretically, the two computation graphs should like simplify to the same thing, right? Because they're computing the same thing, so they should be like equivalent in some way. That was some good apple juice. Grade A. But yeah, I actually have a very strong feeling that if I find an algorithm to do this and do this, oh, I didn't mean to do that. Then I have a very strong feeling that I'll get something that looks a lot like this. But which is a very good sign because like this is heckin' parallelizable, you know? Um so yeah. Uh yeah. I don't know. Yeah, so how do I get an algorithm to like actually do this? I was thinking, what if I just use a greedy algorithm, right? So what if I just set my partitions, um, and then I go through and I can like take a node, right? I can see, yeah, I can like choose one of its connect. Okay, first I start with the guaranteed nodes, which are these nodes that have incoming degree 0, right? Um, I can take these and I can look at their connections. And if there is one that, or yeah, and if adding the connection um, either increases the total amount of nodes or it minimizes the amount of the amount with incoming degree 0, then we add it. I honestly don't have any intuition for why that should work. It just sounds like a graph algorithm. It sounds like an algorithm that you would do on a graph. uh, but I really don't have any better ideas. Yeah, yeah, I don't know. Yeah, it's difficult. It's difficult. Man, I don't know what. How is this? How would this algorithm work? How would this theoretical algorithm work? This algorithm that would just like be magic. This magic algorithm, if you will. Yeah. I don't know. Like Dijkstra's algorithm or something. Yeah, I feel like maybe I just need a way of like reformulating the problem so that I can use like an established graph algorithm. I don't know. It's like vaguely like minimum spanning tree esque, right? Because I'm like, well, it's more like maximum spanning tree. Minimize nodes. Well, okay, so I want to maximize the total amount of nodes, right? So, um, yeah, so I guess maybe I just like iterate over everything, and if adding that node helps me, um, yeah. So if adding a node minimizes the total amount of nodes. Ah, it's so hand wavy. I don't understand how to do this. I'm stupid. Why can't I just have someone who's smart help me? Why why do us stupid people have to suffer like this? It's a curse. Having such good ideas but being so stupid. It's impossible. Uh huh. Hmm. That's what I'd say if I was an anime. Uh Except probably not, because that's what the person who's winning says. And I'm not winning. This is beating me. I don't know, like do I even have like a stupid way of doing it? Yeah, like so can I even find a dumb way of doing it? It's like it's a proof of concept, right? So what if I just like randomly select or I just like randomly divide up all the nodes and then I like so I just choose uh n over 2 random nodes and then random these nodes. I just choose like n over 2 random of these nodes, of like the base nodes, and then I look at all of my n over 2 base known connections, and then I determine if adding any of the connections to the set will help me with this criteria or this criteria. Uh, how could I possibly know? Oh, man, I don't know. Graph algorithm. So yeah, I want to maximize the total amount of knowns, and I want to minimize knowns with incoming degree 0. I want to minimize connections to unknowns from knowns. I want to maximize number of connections between knowns. What kind of graph algorithms are out there? Graph algorithm. Graph algorithm. Graph algorithm. Category graph algorithm. Graph drawing. Network flow problem. What's this? What's this? What is this? What's that? Random scale-free networks using preferential attachment mechanism. What the heck? What the heck? Belief propagation. Some product message passing is a message passing for performing inference on graphical models such as Bayesian networks, Markov. No. No. What's A-star search? Traversal and path search algorithm, which is often used in many fields of computer science, due to its completeness. All generated nodes in memory. Pre-process the graph. Memory-bound approaches. Best solution in many cases. Wow. Whoa. Fascinating. Pseudocode. Okay, yeah, I'm getting lost in the algorithm. Graph algorithm. You know, I'm sure I'll find what I want if I look hard enough. Yeah, okay, what is my algorithm? Like, I'm looking for, like, partitioning algorithms. Graph partitioning. Reduction of a graph into smaller graph. To a smaller graph, partitioning instead of nodes in mutually exclusive groups. Edges of the original graph will produce edges in the partition graph if the number of resulting edges is small compared to the original graph. The partition graph may be better suited for analysis and problem solving than the original. Finding a partition that simplifies graph analysis is hard enough. It's hard enough. I mean, on its own, but with all the other stuff, oh geez, it's a hard problem. But one that is application in scientific computing, yes, that's so true. Oh no. Since graph partitioning is a hard problem, practical solutions are based on heuristics. There are two broad categories of methods: local, global. Well-known local methods and the fiduciary algorithms, which are the first effective two-way cuts by local search strategies. Arbitrary initial partitioning of the vertex set, which can affect final solution quality. Wait, okay, so what exactly is graph partitioning? Are minimum cut and maximum cut problems. There's minimal and some metric. Allowing both positive and negative weights can be trivial transformed to weighted maximum cut problems by flipping the signs in all weight. Oh, fascinating. Without terminal nodes. Is limited to non-negative weights can be solved polynomial time. In the special case when the graph is unweighted, Karger's algorithm provides an efficient randomized method for finding the cut. In this case, minimum cut equals the edge connectivity of the graph. A generalization of the minimum cut problem without terminals is the minimum. Okay, I'm looking at with terminal nodes. When two terminal nodes are given, they are typically referred to as the source and the sink. What? Well, I have multiple terminal nodes, bro. Are you telling me that there's no maximum, minimum cut? What's maximum flow? Did I do this already? Network flow problem. Yeah, what is a network flow problem? Are a class of computational problems in which the input is a flow network, a graph with numerical capacities on its edges. See, I guess I kind of have that, but like not really. Well, so it's like my nodes have a weight, right? My nodes are weighted by how many inputs they have. Well, okay, they aren't really weighted by how many inputs they have. They kind of are. Okay. They aren't in the kinds of graphs that I'm looking at. You could just split it up into an equivalent graph where the nodes are have a maximum of 2 inputs. The problem with that is that there's like a bajillion ways to split it up. Maybe I should do that though. Oh, it's kind of interesting. I didn't think about that. Yeah, maybe I should do that. Huh. And interesting. Yeah, I wonder if that actually makes it like an easier problem to solve. I mean, the main thing is like how. Okay, so I don't know if this matters, right? But it feels like it does, which is if I have an operation f of a equals a plus b, right? It's commutative on its inputs, and it would be associative if I did something else, right? So if I have 3 nodes, this is f1, f2, f3. This is f4. So f4 is equal to f4 of f1, f2, f3 is equal to f1 plus f2 plus f3. Now this can be represented also as something like this, right? Where we have f1, f2, f3, and then we have f4 prime, and then we have f4. So we have f4 prime is equal to f1 plus f2, and f4 is equal to f4 prime plus f3. So we have increased the amount of, well, okay, yeah. So the problem with this is that we can also have something like this, right? Where we have, yeah, and there's even another one, but like this is f1, this is f2, this is f3, and so now we have f4 prime is equal to f2 plus f3, or f2 plus f3, and f4 is equal to f4 prime plus f1, right? These are two like equivalent formulations of the same thing. But would this like affect like an algorithm that's trying to find, like the optimal partition? But yeah, so I don't think that this would be a network flow problem, at least from what I'm reading here. Oh, I just realized. Okay, well, I was saying that like you can formulate it like this, or so you have this problem, right? And then you can formulate it like this, where you split it up like that, or you can split it up like this. But like they're distinct graphs, but they aren't. So, but okay, yeah, I guess here it just kind of depends on your choice of f1, f2, and f3, right? They're I mean, these two graphs are what is it called, like isomorphic or whatever? But yeah. Anyway, I don't know. Maximum flow problem. Yeah. So a minimum cut. Huh. Yeah. Like I don't see. The part of the problem is like I don't know what I'm trying to do. Like I have a vague understanding that I want to maximize these guys and I want to minimize these guys. Well, no. I want to maximize, like if this is our partition, right? Then I want to maximize these guys while minimizing these guys. Like, okay, you know what? Okay, if I say that I have, I don't know, 10 nodes. Oh, what if I start at the back? Right, I start with the I don't know what you call them, the leaf nodes. The nodes at the very end. These nodes right here. Oh, I realize the thing cannot be seen. What if I start with these nodes and then I work my way back? Can I like reason about that somehow? Oh. Can I reason about what those nodes should be? I don't know if I can. Oh, I'm just tired. I want to go to bed. I don't want to think about graphs. Knowledge graph embedding. Feynman-Wong algorithm. Two different algorithms of graph theory solving the digraph realization problem. Yeah, that's probably not related. Going forward, woo! Uh, Foley algorithm. Oh, what a mean algorithm. Yeah. Dijkstra's algorithm. Yeah. See, I don't even know what this problem, like what this kind of problem is. Like I'm trying to minimize nodes with a particular property, and I'm trying to max. So I want to partition the graph in such a way that I'm maximizing the amount of nodes with a particular property, and I'm minimizing the amount of nodes with another property. Right? Like, there are a bunch of different ways. I mean, I guess like, well, no, I was gonna say, oh, what if I just go through all of the ways of explaining a graph? Oh, that's genius. Wow, I'm the smartest guy alive. No, I don't know. What if I just start with a random partition? Yeah, I just start with a random partition, and then I just kind of like evolve into like the best partition. I'm just like, yeah, I just try swapping random nodes from other partitions, and then if that swap would actually increase it, then I keep it, and if it wouldn't increase it, then I search for another swap. Well, yeah, it's not just about increasing me; it's about increasing the whole system. That's an interesting idea. I mean, I guess I don't see why. I don't. Like, it's not immediately obvious to me why that wouldn't work. So the other question is, so I understand what I want to do for a particular graph, but what should the whole system look like, right? Like what should the metric be for actually determining like if this actually helps things or not? Johnson's algorithm. Any angle path planning algorithm that is based on A star, it can find near optimal paths with run times comparable to that of A star. Original graph with negative edges. A shortest path routing. Yeah, I don't know. Yeah, I mean, okay. So I guess let's just start thinking about what I want my thing to look like, right? So I have these. I have these metrics that I want to this is just like it's not set in stone. This is kind of what I'm going for, right? I know that having like having a lot of knowns uh that having relatively few um relatively few what the heck is the word? Relatively few unknowns compared to how many knowns I have is a good thing. That's is probably going to be a good thing. On that same note, having having relatively few or what? Yeah. Okay. Yeah. So having as few unknowns as possible. Um, that is a good thing. Uh, and also, what is a good thing is what is also a good thing. uh, Yeah, what's also a good thing is having oh yeah, okay, so to my knowns, okay, so I want to increase the degree going to my unknowns as much as possible. Let me write that down really quick. Um, Maximize incoming. So yeah, I want to maximize the incoming degree of the unknowns. I mean, obviously, I mean, with the incoming degree uh, within the set. So yeah, I want to maximize the amount of things that go, and I want to minimize incoming degree of un, un unks from outside. So I want to maximize the incoming degree of unknowns from inside. I want to minimize the incoming degree of nodes of unknowns from outside. So nodes that have um, like a high amount of things coming inside from like outside of our partition, that's not good, right? I don't like that. So yeah. Um, hmm. So fascinating. Really is. Okay. So I want to minimize knowns with incoming, maximize incoming degree of unknowns from inside, minimize incoming degree of unknowns from outside. Yeah, I also want to maximize the number of connections between knowns, right? So I want all the knowns to be highly connected. The reason is because I want to keep everything on the DL, you know, you know. No, but no. I I want to increase the density of the graph so that whoever I'm giving this to has to do more computation before they send it back, right? Because the idea is that I'm splitting up this graph, I'm sending it over a network, which takes a while, and then they're like, oh, okay, so this is what I have to compute, and then they can go compute it. So ideally, you would send as little information as possible, and that would tell them like that they like how much information they like. Yeah, you have to like basically. I don't want to say like, oh, compute the first digit pi, compute the second digit pi, compute the third digit pi, compute the fourth. Like I just want to say compute pi, and then I want them to have all necessary information to understand what that means, right? I actually don't think that was a really good analogy, but whatever, dude. Who cares? Leak? Community structure of networks? Oh, okay. What is this? Closure problem. Is a no edges leave C. Fascinating. Hey, it's fascinating. So something else that I really haven't thought about a whole lot actually is like cyclic graphs, right? Because I might have something like this, but then what if we have a cycle, which like I mean that's very very possible, right? Um, so I mean, okay, this actually isn't an accurate picture because what it most likely would be is it most likely would be something like this, where or yeah no like this is the actual structure, right? So these are our actual initial values, and then in the next, so this is like the 0th cycle, right? But then what happens is in the next cycle, now, um, now these values depend on this, right? So this would be like the initialization stage, and then this would be the remaining loop. And like this is like more accurately what happens in a neural network, right? Like you calculate the loss, and then you do some more calculations to get the gradients, but essentially the value here would then depend on the loss, right? But I don't know. This isn't really accurate. Yeah, I actually not. Yeah, I actually don't think it would be useful to model it as like a loop. I think it would be a lot more useful to model it as just like one continuously flowing graph. And so instead of that, like this would just fly off screen again. Like yeah, so these would basically be epics, right? Um, yeah, more accurately, I guess, is something like this, right? Where you have this kind of structure instead, where like these are your initial unknowns, and then yeah, and then you would say, oh, okay, I'm gonna run it for this long, and then that's gonna happen. Yeah. See, this is probably more so than the network that we'd end up seeing. But yeah. Okay. I think next time I come back to this, I'm going to take my just my basic matrix multiplication graph, and I'm going to try implementing that naive algorithm that I stated. So I'm going to write that down. Start with random even partition and try swapping random nodes between partitions. If health improves, keep the swap. Yeah, I think that's really so. yeah. And then I guess what we have to do is we just have to like figure out what like what is our exact health metric, or like what ratio or whatever are we using precisely to like determine the health of the network. So yeah, I think that was it for tonight. Um, but yeah, I'll come back to this tomorrow or the next day or something. I have no idea. I will see.